Hi, hello, welcome to part 2 of chapter 8. In this section, we are going to talk about a topic called combustion analysis and how it is useful to identify the empirical formula as well as the molecular formula given certain information. Okay, what it leads to is how atoms are related to each other in terms of mass, and also you can see the influence of law of conservation of mass theory. In the previous part where we discussed about balanced chemical equation, we stressed on law of conservation of mass theory by seeing that matter cannot, by making sure that you have same number of atoms on both sides. What it literally means is whatever the total amount of mass you started with, you should end up with the same amount of mass you end up with, right? So based on that, we used it. Well, right now we know we have so many techniques that you can easily identify how much of mass a certain element has, for example, using mass spectroscopy. But in the past days, people have to do different techniques to identify molecular formulas. So one of that application of that technique is combustion analysis. What you basically do is you will collect the sample that you want to try to identify the empirical formula of a sample for, and you kept that sample in a closed chamber like this, and you combust it in the presence of oxygen, and you will have a different absorbers for different compounds. Combustion has only unique products, both CO2 and H2O. So you have both CO2 and H2O absorbers. And this copper oxide serves to make sure only H2O and CO2 passes through, but not the byproduct of that reaction. Sometimes that forms as CO instead of CO2. So it makes sure that all of the CO also absorbed are converted back to the CO2. So how do they do it? If at all anyone is curious, is they have the masses of these absorbers before and after the chemical reaction, and based on how much of that weight difference is, they could tell how much of H2O and CO2 is produced. Okay, so using that, let's try to identify empirical formula of a glucose. So like provided you need to know certain information, right? Certain information is you need to know what compound it is, glucose. And you need to know what is the approximate ratios of the formulas that you have. You expected to have carbon, hydrogen, and oxygens, but we don't know the ratios, but you expected to have 3 atoms. And you were told that you were starting that combustion analysis with 18.8 grams. And when you do that, after the combustion analysis, you produced 27.6 grams of carbon dioxide and 11.3 grams of H2O are produced. Okay, so using this information, let's try to identify the empirical formula of the glucose and eventually maybe the molecular formula of glucose, right? So this is what you have to do first. First, you need to identify masses of individual atoms in the product. What you were given is mass of compounds that are produced, but not masses of individual elements. So we are going to identify mass of individual elements starting with carbon, hydrogen, and oxygen. Okay. So we are going to identify mass of carbon, and this is when I said you need to have the good, strong commanding techniques on how to convert moles to mass, moles to moles, because from here we are going to use it a lot, very frequently. So to identify, excuse me, to identify the mass of a carbon, so you're going to take where the carbon is present in the carbon dioxide, and there is 27.6 grams of carbon dioxide is formed. So what we are going to do now is we are going to first identify how many moles of carbon dioxide is present in 27.6 grams of CO2, and based on the ratios of in CO2, excuse me, and in CO2 we know that for every 1 mole of CO2, there is 1 mole of carbon and 2 moles of oxygen for every 1 mole of CO2. That is how we read a molecular formula. In that ratio, they combine. So using that ratio of 1:1, we are going to identify moles of carbon, then convert it back to grams of carbon. Okay, that's going to be our plan. So from the mass of carbon to the moles of carbon, excuse me. Let me just write it. I think initially I need to take it slowly with you guys. So from grams of CO2, we are trying to go to moles of CO2. And because in moles of CO2, you can tell the ratio of carbons in each one of the CO2 molecule, you are going to identify moles of carbon. And because you know the molar mass of carbon, from there, you're going to identify grams of carbon, which is what you need. Okay, to reach to the grams of carbon, that's what you have to do. Convert the grams of CO2 to moles of CO2 and moles of CO2 to moles of carbon, then identify grams of carbon. So from here, you can cancel grams of carbon. It should say CO2. Mistake. Grams of CO2 to grams of CO2, and then you are going to use the conversion factor of 1 mole of carbon over 1 mole of CO2 to cancel the CO2s, and you're going to convert the 1 mole of carbon with the carbon molar mass, and you're going to end up with the units of grams of carbon. And we are going to do the same to hydrogen as well by taking the mass of water as 11.3 grams. And you can frankly pause the video and start doing it by yourself, but I'm going to go over it again. So the plan is going to be just like I said, because this is what we're going to use. This is what we have to do. We have to start with grams of H2O, mass of H2O, convert to moles of H2O, and in water, in each one water molecule, there are 2 moles of hydrogen. So using that relationship, you're going to convert to moles of, I shouldn't write 2 there, I don't need to. You're going to identify moles of hydrogen and then 2 grams of hydrogen because you need mass of hydrogen. So that's going to be our plan, and that is how we are going to achieve it. Starting with the grams of hydrogen. To the typo here again, sorry. That should read it as H2O. Okay, and once you cancel the grams, you're left with the units moles. So moles and moles are cancelled. So see here, for every 1 mole of H2O, there are 2 moles of hydrogen. So you're going to cancel the moles of hydrogen with the moles of hydrogen molar mass conversion factor to end up with the mass in grams. Okay, let me just erase this thing to have more text information there. Now that we identify masses of carbons and hydrogens, and you already know what is the starting mass you started with, here you can just subtract the mass of carbon and hydrogen from the mass of glucose to get the mass of oxygen, which is what we did to find the mass of oxygen as 10 grams, which is sweet. So now you know the masses of carbon, oxygen, and hydrogen. So now we're not done yet. This is a long process because we are trying to identify the coolest thing, the empirical formula of a molecule. So far you have the masses of carbon, hydrogen, and oxygen. So what are you going to do with this is you're going to convert them back to the moles and compare which moles is in similar ratio, which moles is in excess ratio using a technique. Now, let's do the math again. Let's convert all of these masses into their individual moles. There are 0.627 moles in 7.53 grams. and there are 1.25 moles in 1.26 grams, and there are 0.626 moles in 10 grams of oxygen. Okay, so now once you know all of these moles, to identify the empirical formula, the smallest ratio, you're going to take the smallest moles over rest of the moles to identify ratio of one to another. And this is how we do it. So 0.627 is the smallest ratio moles, or 0.626, and you're going to take it over another. So once you cancel these ratios here, you get 1 carbon. Once you cancel this, you get 2 hydrogens. Once you cancel this, you get 1 oxygen. That is how you identify empirical formula as CH2O. And using the empirical formula, you could even identify molecular formula given you were told what is the molecular weight is. Okay, if you know the approximate molecular mass. Let's say you were told that it is glucose and it has molar mass of 180. And what you can do to identify molecular formula of glucose is you're going to take the empirical formula mass, and you're going to take the glucose molar mass, and you're going to take in what ratio they were present in excess, right? So the empirical formula mass is 30 grams per mole, whereas the actual glucose molar mass is 180 grams per mole. So to identify in what ratio carbon, hydrogens, oxygens is present in glucose, you're going to identify the ratio between empirical formula mass and molecular mass. So the ratio is going to be 6 times. So you just multiply your empirical formula with that 6 to identify actual molecular formula of glucose. That is how you do it. That's all you need to learn for this topic, but I still have one more example that I want you to practice by yourself. So what we did so far, we just learned how to identify empirical formula using a tool called combustion analysis. So what did you do there? You took the whole mass and you taken the products, and using the products, you identify individual masses of atoms like carbons, hydrogens, and oxygens. And using that, you convert it into moles, and they have taken the ratios between moles to identify empirical formula. All right, and I want you to try this problem on your own, right? You just saw me going through the problem, and it is very similar problem. I want you to try it on your own. So problem is saying there are 5.5 grams sample of benzene, okay, and it produces 18.59 grams of CO2 and 3.81 grams of H2O. Okay, so determine the empirical formula and the molecular formula of benzene given that its molar mass is approximately 78 grams per mole. Okay, so now plan is same, just like the previous problem. You're going to identify individual atoms, masses present in the products. There are 2 products, CO2 and H2O. So you're going to identify individual carbon mass, individual hydrogen mass, and individual oxygen mass by taking the difference between carbon mass, hydrogen mass with the starting sample of 5.5 grams of benzene mass. Once you do that, you're going to identify the moles of those carbons, hydrogens, oxygens, and identify the ratios between them using the smallest molar quantity. Okay, exactly like in previous problem. So let's start with identifying the mass of carbon using the mass of CO2. So there are 18.59 grams of CO2, and using the molar mass conversion factor, we will identify how many moles are there, canceling the grams, and using the ratio between moles of carbon to moles of CO2, you will cancel out the moles of CO2 to get the moles of carbon, and using the molar mass conversion factor, you cancel the moles of carbon to get the grams of carbon present, 5.07 grams of carbon. And you would use the same technique on hydrogen to identify the mass of hydrogen present. So in 3.81 grams of hydrogen, excuse me, 18.01. So 1 mole of H2O weighs 18.01 grams. You cancel out the grams to get moles of H2O. And to identify moles of H2O, you use the conversion factor between 2 moles of hydrogen versus 1 mole of water, and you get the moles of hydrogen. But to get the grams of hydrogen, you need to multiply with the molar mass conversion factor of hydrogen. So you get mass of hydrogen. Now to identify how much of mass of oxygen is present in that formula, you subtract masses of carbons and hydrogens from the given mass, which happen to be exactly same, 5.5 grams, and you already sums up to be 5.499 grams, which means there are no oxygens in that given chemical formula. So apparently benzene just had carbons and hydrogens, and we don't know what is the ratio is. On the next slide, I have answer waiting for you. Let me pause the video and correct. So let's get to work. Let's identify the empirical formula and molecular formula of benzene. So here, what we're going to do is you're going to identify moles of carbons present in the identified mass of carbon. There are 0.424 moles. And we are going to identify how many moles of hydrogens are present. There are 0.423 moles of hydrogen. Now, those numbers are pretty close to each other, which means they were in 1:1 ratio, both carbon and hydrogen. So the empirical formula is CH. CH. Now we were told that molecular mass of benzene is 78, and CH is going to weigh about 13 grams. 78 over 13 gives about 6. So you're going to multiply CH with 6. So you will end up with the molecular formula of C6H6 like that. That is how you would use the combustion analysis technique to identify the empirical formula and the molecular formula of a compound. That's all for this topic, and I'm sharing the screen. Yes. That's all for this topic, and I will see you guys in the next topic.